Hello students, today we want to take our knowledge of gravity and talk about why gravity explains the motions that we see in space. Asking ourselves the big question, what factors cause observed motion in space? So first recall that gravity is a force that only pulls objects towards one another, and what causes gravity is an object's mass. So when an object has mass, it causes a gravitational pull. We know that gravitational force acts between any two objects. They'll create a pull on one another, as we see in this model here. If mass increases, the force of the gravity also increases. If distance increases, the force of gravity decreases. These are some essential concepts that we're going to be using today to explain the observed motion in space. I want you to take a look at this video, and as you're watching, I want you to take some observations. What are some common characteristics, some common themes that you're seeing as you look at these various images? In the video, you saw a lot about galaxies, and I want to take a moment to define what galaxies actually are. A galaxy is defined as a system of millions or billions of stars held together with gas and dust, held together by gravitational forces. So recall that a galaxy is a system, and a system is anything that functions together. So you have many components working together for one thing. The thing that makes up a system in a galaxy is the stars. Millions and billions, not just one star, but millions and billions of stars. They're mixed in there with gas and dust, and they're held together all by some type of gravitational force. Here's a picture of what a galaxy might look like. There's a few different types of galaxies that we'll be going over in just a few minutes. Breaking down this definition, I want you to think, how would you describe a galaxy in your own words? The Milky Way is the galaxy that we on Earth live in, and there's many other systems within our own galaxy. But you could see on this diagram here, our little solar system within the Milky Way galaxy. So we're just a really, really small component of one galaxy. You can also see, if you look in the night sky on a clear night, you can kind of see the Milky Way galaxy. Now remember, we're in the galaxy, but you can see parts of it. Also recall that a solar system is when there is a star with planets that are orbiting that central star. So we have a solar system of a total of 8 planets. Thinking about the differences between a solar system and a galaxy, I want you to take a moment to think, why are galaxies and solar systems different? I also want you to think about, why are galaxies and solar systems similar? Here we see 3 specific types of galaxies. Picture A is a spiral galaxy, and these galaxies have a bulge in the center and arms that spiral out like a pinwheel. Some of the attributes of a spiral galaxy are bright young stars. We see lots of gas and dust. We also see the formation of new stars. Notice the Milky Way galaxy is a type of spiral galaxy. An elliptical galaxy has shapes that are round, like a ball or an oval, and their attributes have little gas and dust. They vary in sizes, and they no longer form new stars. Therefore, we can conclude that elliptical galaxies are the oldest types of galaxies. And then finally, our third image here are irregular galaxies. And these are similar to spiral galaxies, but they do not have regular shapes. So they're typically smaller, lots of gas and dust, and they also form new stars. I want you to take a moment to think, what are some similarities between these types of galaxies? So keeping in mind some of our different types of galaxies, I want to take a moment to take a step back to talk about what is gravity's role in the formation of these galaxies. So we're going to look at some data tables here, and I first want to focus on the mass of these objects. So in this system, we have 3 objects, objects A, B, and C. And we're given the mass in billion kilograms. So first we have 100,000 billion kilograms for object A. The mass of object B is 500 billion kilograms, and the mass of object C is 800 billion kilograms. So based off of this data table, which object would have the most gravitational pull and why. When you think about that, we know that two things affect gravitational pull: mass and distance. The greatest mass here is object A, therefore object A would have the greatest gravitational pull. The least gravitational pull would be object B, because that out of the three objects has the smallest mass. However, we also know distance plays a role in this. So let's take a look at some distances. Notice the distance for object A is 0. And that makes sense because if this is a system, object A was the one with the most mass, that would be our central star. That would be the object creating the greatest gravitational pull, therefore the other objects would most likely orbit it. Object B has a distance of 10 million miles from the star, and object C has a distance of 6 million miles from the star. I'm also putting in some information about volumes. Remember, volume is how much physical space something takes up. So the more volume, the larger the actual physical space of the planet. So if we were to think about which planet would be the largest, then we take a look at our three options. We would know that 5 trillion miles cubed would be the largest. So object A would be the largest. The smallest out of these options would be object B. We also have some information about the time of orbit. So how long does it take for this object to fully revolve? One full orbit. Again, object A is a central object, so it's not going to have an orbit. But object B and C both have an orbit. We can conclude that this makes sense. We see a correlation between the distance from the central star and the time it takes for the object to orbit. Notice the greatest amount of distance would make sense. It would take the longest for it to have one full orbit. Let's take a look at another data table here. So based off of this data table, which object would have the greatest gravitational pull? Because object B has the greatest mass, it would have the greatest gravitational pull. Which object would have the least gravitational pull? Because object A has the smallest mass, it would have the least gravitational pull. Which object is farthest away from the central star? Because object C has the greatest distance at 1,000 million miles, it would have the greatest distance from the central star. We can also predict then that because object C had the greatest distance, it would also take the longest to orbit. Taking a look at some of the volumes here, which object would be the largest? It makes sense that the object with the most mass would also be the largest. Not always necessarily. You saw yesterday that sometimes black holes are not that big, but they're still very powerful. In this case, object B would be the largest because it takes up the most volume. The smallest would be object A. The time of orbit, how long it would take for the objects to get around. Well, we said there's a correlation between the farthest object and the most amount of time it would take, which we see that correlation here once again. Object C is the farthest away. It also takes the longest to make a full orbit or a full revolution. Looking at a more complex data table here, I want you to take a moment and draw 3 conclusions based off of this data. So take a moment to look closely at it. I'm going to break down that data table for you. One of the things that we saw was that revolution or orbit is that how long it takes for an object to get around the central star. We know that in a solar system, the closer planets are going to orbit faster than the outer planets. So when we look at the period of revolution, I want you to make an assumption or prediction about gravity. Taking a look at just the period of revolution, what do we already know about gravity, and why does this happen? So taking a look at this data table here, you can see that Mercury, the closest planet, only takes 88 days for it to fully revolve around the sun one time. And we see that there is an increasing trend. So as we move down the list, we see that it takes longer and longer per planet. Why do we know this? Well, because the more distance, the less gravitational pull. Let's take a look at the mass now, and this is measuring mass as in if the Earth equaled 1. Based on what you already know about gravity, what conclusions can you make? The first thing that stands out to me is that the Sun is way more massive than any of these other planets, which makes sense that that would have the greatest gravitational pull. I also note that Jupiter is the largest of the planets. Jupiter has a pretty strong gravitational pull as well. If we were to diagram out these planets, put them in the correct order based off this data table, how would you arrange these planets? Notice this time we don't have the distance from the central star, but what we do have is the period of days. And we said there's a correlation between the period of days it takes for a planet to revolve and how far away the planet is. So if a planet doesn't take very long for it to fully revolve, it's going to be closer. There's less distance. If it takes a long time to revolve, there's greater distance. These two factors help us understand the motion that we observe in space, answering today's big question. Thank you.